Now we will move on to look at titrations involving a weak acid or a weak base. We'll only be covering titrations where we're using a strong acid or base in the burette, as this tends to be the most useful. We'll review the basics of what is occurring during a titration and talk again about how to tell what is being titrated and what that is likely being titrated with. The main part of this video will be determining the pH at any point during a titration. These tend to be relatively long problems, and that's why we're going to work through it in great detail here using two different methods so that you can decide which way you like it the best. We already discussed this a bit, but I want to review what exactly is happening during a titration. We have an Erlenmeyer or a beaker, some sort of glassware sitting on the bench, and that holds what we call the analyte. Generally, we don't know something about it. Typically, that either involves the concentration or the moles or the purity. Most of the work that we'll be doing will involve finding the concentration. It's good to be able to figure out what the pH of this is going to be at any point. In a different video, we'll talk about how to use the equivalence point to find information about the analyte and how to use it to find purity and many other things. In this section, what we're actually going to focus on is just finding the pH during different parts of the titration. While in reality in a laboratory setting you would be measuring these, it's really important to be able to go through and do this because it shows that you know exactly what is occurring at each step of the titration and how to solve it. Whenever we go to solve a titration curve, we need to establish which type of titration that we are dealing with so that we know how to continue the problem. In this case, we've started out with a weak base, and we're titrating it with a strong acid solution. Let's walk through all of them together though, because it's possible that if you were doing this in a different type of setting, maybe you have the curve and you don't know what the analyte is. So the first one that I have shown here, we can see where our pH starts, and it's at a basic pH, and so that's got to be a base. You know that it has to be a strong base because there's no buffering region. The same thing is true with a strong acid. It starts at a low pH this time because it's an acid, and we don't see any buffering region. So we know that it must be a strong acid. This is what this section will focus on though. If it starts at a high pH and then levels off right here, that is what we call a buffering region. That leveling off is the buffering region and only happens if you have a weak acid or base. The weak acid is very similar. It of course starts at a low pH, and you know that it's weak rather than strong because this region right here is the buffering region and only occurs when you have a weak analyte. Let's look at a couple of really important areas of this curve. Right here, we have what we call the equivalence point. We're going to do a bunch of examples involving the equivalence point in other areas of the class. We have another point which is the halfway to the equivalence point. This is an important point because this is the point where our pH is equal to our pKa. We can see each of these on the weak base as well. We have our equivalence point, we have our halfway point to equivalence, where our pH is equal to our pKa. In our situation, this is what we will be dealing with. We have a weak base titrated with a strong acid. We will do two approaches to these problems. The first one requires that you have a pretty good understanding of what you are doing before you start the problem. It's much faster and it's much simpler once you get the hang of it. However, it does involve a fair amount of memorization at the beginning to know what you're going to do at each step of the titration curve. In another case, what we will be doing won't require that level of knowledge, and we'll walk through the same protocol each time on finding out how much of each species we have in solution, and once we do the reaction, we will then decide what to do with the problem. It's much longer, but it's also a bit more formulaic and a bit easier to understand in the beginning. We'll start with approach 1. This is the one that is typically taught in textbooks. Honestly, I have found that students don't tend to love this way because it does involve that large amount of knowledge that you're starting out with, and that's sometimes a rough starting point. So we're going to start this way because it's the typical way that it's taught, but know that we'll go into it in a bit more detail, and this might make a bit more sense once we do approach 2. So if we're here, our first step is going to be establish which titration we're dealing with. That's really a good set of first steps regardless of what you're doing, so that's why we've already covered it. In this case, you're going to need to find the equivalence point. That's because it's going to tell us how to handle every other part of the problem. It's going to tell us where we are in the titration curve and what type of solution we are dealing with. Now, once we've done that, if we are looking for the pH at a point that is before the equivalence point, we'll have a buffer. If we're looking at it at the equivalence point, it will either be a weak acid or a weak base, depending on what the titration was. Or if we're looking at it after the equivalence point, we'll actually treat it like a strong acid or a strong base. This will make more sense when we actually go through the problem. Once we have that decided, we'll treat each problem just as we did in previous simpler problems through the last 2 chapters. So let's start by finding our equivalence point. Even if you plan on doing all of your problems using the later solution method that I'll show you, it's still needed to be able to find the equivalence point. So make sure you can do this regardless. The reason we want to know this is if we know where this point is, at what point in the graph this is, we will know that if we are before that point, we are in the buffering region. If we are here, we have a weak acid. Or, of course, if we are just starting out, we have a weak base, since that's our starting solution. And then if we're out here, we will have a strong acid. Again, if this isn't making a lot of sense to you, once we actually walk through it the longer way, you'll see why. So why do we want to look for how do we look for the equivalence point? First off, let's talk about what it is. This is the point where the amount in moles of the analyte, or the thing in the burette, is equal to the amount of the moles of the titrant, the thing in the beaker. Now, let's be really careful here with how I say this. It's the amount of the analyte that is added is equal to the initial amount of the titrant. Because of this, we can set up a situation where we have our moles of acid are equal to our moles of base. Just be really careful when I say moles of acid are equal to moles of base, that you remember that it's the amount that is added as compared to the amount that you initially had, not the amount that's in solution at the given time. Now let's do this for our problem. We'll set up our moles of acid. Our moles of acid are equal to our moles of base. So here M is just concentration, V is in volume. We'll fill in our values. Here we have our 0.2 molar in our unknown volume. This will be our equivalence point volume. Here we have our amount of NH3 that we started with and our 10 mils that we started with. We're able to leave this in mils because we have the same units on both sides. So whatever unit we put our volume in on one side will be the volume that comes out on the other. We solve for this and we get 15 milliliters, which means that this point right here, our equivalence point, is at 15 milliliters. Now let's talk about the step that involves deciding which part of the graph that we're on. We decided that for this problem, our equivalence point was at 15 mils. From here, we can tell which part of the graph we're on depending on how many mils of acid was added. So in the very beginning, we simply have a weak base. This is our NH3 solution. When we go to solve for the pH of that, it's simply an NH3 solution, just as you knew how to do weeks ago. When we get to this section though, now we have a buffering region. And that's because much of the NH3 has been reacted in forming NH4. So now we have two things present. We have NH3 and we have its conjugate acid. As we continue to add more and more strong acid, more of the strong acid reacts with the weak base, and this leads us to the equivalence point. And at the equivalence point, everything has been converted into NH4. This happens when the amount of the strong acid that you have added is equal to the initial amount of weak base. Now lastly, as you get further along in this curve, now we have two things present. All of the base is used up and turned into NH4+. However, we've then added even more acid. And because of that, most of what changes the pH is the strong acid. And so we actually will end up treating this as a strong acid problem. So now let's try both of these. Let's start with our 0 mils added. At 0 mils added, we're at the very beginning of the titration, and we simply have a 0.3 molar solution of NH3. This is not any different than all the problems that we have been doing for the last couple of weeks. We have our weak base, and it's going to react with water to form its conjugate acid. From here we make our ice chart. We fill in our values. I'm going to be a bit lazy with significant figures and units in order to fit everything in a bit easier, and then we'll take care of that later at the end. We know that it's going to change by some amount, and so we use x. We of course can look up the Kb. Since this is a base equation, we're going to use the Kb. Now, we have a quadratic, which isn't the nicest thing in the world to have to solve, so let's look at our concentration and our Kb and decide if we think we can make the weak acid assumption. It looks like we should be able to. From here, we have a much simpler problem to solve. We have our concentration, and since we're looking for pH, we know that we have our concentration of OH-. We don't have H+ here, so we have to be a little bit careful. And remember that this is also equal to 14 plus the log of OH-. We fill in our x value to get our pH. Let's check and make sure it makes sense. We have a relatively concentrated weak base, and we have a very high pH. So that makes sense. Now, for the next part of this problem, I ask you to do the pH at 10 mils. Now we know that the equivalence point is at 15, which means that at 10 mils, we're not at the starting point, but we're also not at the equivalence point. This is the area where we know that the initial NH3 that we started with, some has been converted into NH4+. And because we have both NH3 and NH4+, we must have a buffer. So here, we can use the Henderson-Hasselbalch equation. I would suggest doing this in moles. Be careful when you go to solve for pKa. Make sure that you include pKa, not pKb. We'll need to convert Kb into Ka. We can now fill in our pKa, and we can fill in our amount of base. Again, I would suggest doing this in terms of moles. We initially start with 0.003 moles of NH3, and then we react away the amount that we add of HCl. Since we added 10 mils of a 0.2 molar solution, we are left with 0.002. Similarly, we started with no HA, and we added the amount equal to the amount of the strong acid we added. From here, we plug into our calculator to get our answer. Let's make sure this makes sense. In the last slide, when we started, we had an 11.4 pH. We added strong acid, which was converted into a weak acid, leaving us with a pH that is lower, but not too much lower. Let's move on. At 15 mils, we have now reached the equivalence point. The amount of strong acid that we have added is equal to the amount of weak base that we have started with. What this means is that at this point, every bit of our NH4 or NH3 has been converted into NH4+. And that is the solution that we have. If we only have NH4+, we will treat that as a weak acid. When you go to make your ice chart for this, you need to be very careful to adjust for changing concentrations. When we started, we had a 10 ml solution and a particular number of moles of NH3. We still have that same number of moles of NH4. However, now it is in 15 mils plus 10 mils. And so when we fill into our ice chart, we will need to account for that by dividing the amount of moles by the new volume. You can also do this using our typical way of doing dilutions, which is M1V1 equals M2V2. I'll do this off to the side. And we have 0.12 molar. From here, we continue the problem just as every weak acid problem that we've done over the past few weeks. We fill into Ka. We can again go ahead and say that our weak acid approximation is true and get rid of the minus x, making our calculations much easier. From here, we'll solve for x and use the fact that x is equal to the hydronium ion concentration to solve for pH, using pH is equal to the negative log of x. We can see now that while we started with a weak base, we used HCl to convert all of that weak base into a weak acid. And we see that our pH is in fact lower than 7. That's because we had a weak acid solution after we converted all of our weak base into a weak acid. All right, one more step for this method, and then we'll start over with the other method. At 30 mils, we've now moved past the equivalence point. We used up 15 mils worth of our strong acid by converting our NH3 into NH4. After that, we just continued to dump HCl into the solution. What we'll want to do then is find out how much excess HCl is still present, how much after the equivalence point is present. This is actually just a dilution problem. We first need to find how many mils past the equivalence point we went. We started by adding our 30 mils in, but we know that it took 15 mils to reach the equivalence point, leaving us with 15 mils past. All of the H that was present from this 15 mils excess is still there as H3O+. Now what we'll do is we'll say this 15 mils diluted into the entire beaker, what is that concentration? We'll solve for this using M1V1 equals M2V2. Again, for our first one, we simply fill in the excess. Here we're going to add up our total volume, which is 30 plus 10. 30 plus 10. We solve for M2, and that is our amount of excess HCl, so we can plug that in to our typical pH equation. And if you're saying, but wait, what about all of this, the weak acid that is still in solution? What about the NH4+ that was here and hasn't gone away? Yes, that's still there, but it's not affecting the pH very much. Since it's not affecting the pH very much, we don't talk about it. We can just ignore it. We can say that the amount of this excess HCl makes all of the difference and stop there. Now let's do this a different way. This is a way that I started teaching after working through titration problems with students. I found that in office hours, students were not understanding how to tell which type of solution we were working with. And even if they were able to memorize how to do the problem, they weren't actually understanding why that worked at each point. So to do that, we started going backwards and starting from the very, very scratch and talking about what is actually reacting together. Now, so to do this, I left step 1 the same, That's just mostly because it's a good idea to know. But meanwhile, the rest of this change. So instead of working through and trying to figure out which section of the titration curve you're in, we're just going to start not knowing that. We're going to write an equation that talks about how the titrant and the analyte are reacting together. They're going to react to completion, and then at that point we'll set up an equilibrium if need be afterwards. So we'll make what I'm calling an ICF chart. Now, all that really is a way of me keeping track of moles and doing a limiting reagent problem. Notice I said F, not E. This wouldn't be an equilibrium. This is a full reaction that we are going to say goes to completion, at which point we will decide what kind of solution we have and decide if it's going to create an equilibrium. We'll then look at what's left over and decide what we have. If all we have is a weak acid, we'll treat it as a weak acid problem. If all we have is a weak base, we'll treat it as a weak base problem. If we have both a weak acid and a weak base together, it's a buffer. Or if we have strong acid or strong base, we'll end up treating the problem like a strong acid or strong base problem, ignoring the weak acid or base that is also in solution. At this point, we're going to be back doing the problem how we did it previously. I will go ahead and complete the problem again, but I'll probably go relatively quickly through that part since we've already done it. So let's do this again. We'll do the exact same problem, and I'll just walk through the earlier steps of figuring out which kind of solution you have. Let's start with 0 mils. At 0 mils, nothing has happened. And so I'm not actually going to completely redo this one for you because there's not really much to talk about. All we have to worry about is the fact that this is the only solution we have. No reaction has taken place, nothing has happened, and so the only reaction that we have is NH3 plus H2O making an equilibrium. Since this didn't change at all, I won't bore you with the solution and will just tell you to refer back to the earlier part in the problem. Now's where things get a little bit more interesting. Now let's look at 10 mils. Maybe we don't know where this is. Notice when we went to do this problem, we never actually figured out where the equivalence point is. We know that from an earlier standpoint it's 15 mils because we've already done that part of the problem, but we don't need that to solve the problem in this way. What we need to know is that we initially had NH3, and that NH3 had HCl added to it. I'm going to go ahead and leave the HCl as H plus since we know that HCl or that Cl minus is a spectator ion. Whenever we have a strong acid and a weak base in solution together, they're going to react to completion. Let's keep track of how many moles we have now. We initially had 10 mils of 0.3 molar, which leaves us with 0.003 moles of NH3. And then we added 10 mils of a 0.2 molar solution of HCl. This leaves us with 0.002. Let's make a little note that all of this is in moles, not molarity. We had no NH4 to begin with. This should start looking familiar from the buffer problems that we've done earlier. One of these is going to go to 0. Which one? Well, the one that goes to 0 first. So the 0.002 is the lower number, and so this one goes to 0. So we've done a limiting reagent problem now. Now at this point, we need to say what type of solution do we have, and then we're going to treat the problem as if we are dealing with that type of solution. We look and we see that we have the weak base, and we also have the conjugate acid in solution. Whenever you have a weak base and a conjugate acid in solution together, we know it's a buffer, and so we know that we'll use a Henderson-Hasselbalch equation. Note that we did the pKa the same way that we did in the earlier problem, so you can go back and double check that in that section if you'd like. We get our answer, and we're all done. We never had to know that this was a buffer because of the equivalence point. Instead, we saw that once we reacted them together, we had both the conjugate acid and base pair, And then we could decide that based on that we had a buffer and continue on just like the earlier problem. Let's do the next one. Again, we're pretending that we don't know anything about this particular problem, that we are not aware of where the equivalence point is. So we'll start out the same way as before. That's the great part about this section. We can start out the same way every single time. Just like before, we do a limiting reactant problem. We write our initial amount of moles. I'm going to go ahead and write moles off to the side so that we know to be careful. We send one of them to 0, but in this case, because they have the exact same amount, they will both go to 0. Now let's look at this and decide what type of solution we have. We don't have any weak base in solution anymore, so we no longer have a buffer. All we have is NH4+. So what we have here is a weak acid problem. And we treat it as a weak acid problem. We write our weak acid equation, we write our ice chart, and we fill in our initial values. When you fill your initial values in here, it is generally a good idea to fill it in terms of concentration. Because when we fill into Ka or Kb or any other K, we need concentration. So therefore, we want to make sure that we know this. And this is going to be 0.003 divided by the total volume. So we started with 10 mils and then we added 15. This gives us our same equilibrium line that we had earlier in the video. And we do the same thing that we did before, which is to fill into Kb. We can once again make the weak acid approximation and assume that this x is very small, leaving it as x squared over 0.12 and solving for x. Now, I do mention again that I'm going relatively fast through this section, and that's just because we've already done this whole part earlier in the video. The new part is this. The part where we're, instead of having to decide up front what kind of solution we have, we actually decide by looking at the moles and deciding how they react. Now let's do the 30 ml one. We start out the exact same way. It's the beauty of this way. We once again send the low one to 0. Now this time, our weak base is the one that goes to 0. We should be careful to write moles out here, just so that we keep very good track of exactly what we are doing for units. We now look at our solution to decide what we have. We have both a strong acid and a weak acid in solution together. When you have a strong acid and a weak acid in solution together, generally the only thing that will affect the pH appreciably is the strong acid. And so we calculate our pH based on this, and we say that this we can ignore. And so when we go to find our pH, we simply use our 003. Remember that this is in moles though. And when we solve for this, this is pH of the negative log of H plus concentration. And so we need to divide by the volume. And this comes from our initial 10 ml sample plus our 30 mils that we added equals 40 mils, which is equal to, and we get our pH. Notice all of the answers came out the same, and in each case the second part of the problem was relatively similar to what we had done in the method 1. Doing this step takes a little bit longer. However, it does make it a very general situation so that you don't have to make a decision about what sort of problem you're using before you start solving it. Which way you use is completely up to you. I have no preference either way. The first way we walked through is actually much faster once you get the hang of it, but the second way seems to be a little bit easier for students to understand. So that being said, go back, watch the first way one more time. Maybe watch it through on double speed if you want, and check and see if you can now see where all those pieces are fitting together. And if you're starting to see where all those pieces are fitting together, perhaps you should start doing it that way because it is quicker. If you really just can't see it, that's okay, that's fine, that's not a big deal. Do it this way then, so that you understand what is happening and that you're not just memorizing the techniques for solving the problems. Now, we're not going to go through it, but going through and doing a weak acid titrated with a strong base is basically the exact same idea. I'm going to have your TAs do one of them in discussion. I'm just going to make one note here that the major change is that because you're starting with a weak acid, you're starting out with HA, you're reacting it with a weak base, and so everything is just reversed because you have your weak acid, you have your weak base, and so here you'll have a weak acid problem, here you'll have a buffer problem, here at your equivalence point you'll have a base, a weak base, and here you'll have your strong base problem. Or you can go through and do it like we did in approach 2, each time calculating exactly how much of each species you have left over and deciding what type of problem you have. But we'll save that for discussion. So in review, now you can walk through and decide what species are present at each point in the titration. We did that in the very beginning. Don't forget that that's an important part of this section. Being able to walk through and say what species are present at each point in the titration. Then the major part of this video was looking at how you calculate the pH at each point. I taught you 2 different ways to do this, one of which you have to know the equivalence point for, and then you can decide which part of the graph you're in. And another one where you just react each species that are reacting, do a limiting reagent problem to see what's left over, and then based on what's left over, decide, do you have an equilibrium? Do you have a buffer? Do you have a weak acid? Do you have a weak base? What do you have? And then treat it like the problems that we've done of that sort before.